Very straightforward few slides regarding tolerance stack up. It's very important for any uh, mechanical engineer for day-to-day life, and it's very common to ask some questions during interview about tolerance stack up. I will go over a brief problem and how do we approach tolerance stack up. It's very straightforward, so nothing very complex about it. Uh, this is just a hypothetical question. So let's look into it. What's the question is? Uh, the highlight of the question is that lid is not closing, and how it is framed. It is like recently it came to attention that in a next generation product, hypothetical product ABC, lid is not closing. On further investigation, it was found that this issue is only present in some of the machines, and mostly it's due to the interference which is preventing the lid from closing. Further, uh, like the key question is how do you resolve the issue? And let's look at this problem. How does it look like? So we are given this particular diagram, which this is a particular lid. When it is open, as you can see, it's hanging. This is like the lower part of it. The blue part is like an enclosure, and inside these are like several components. And when lid closes, so when this black part touches this blue part, there is supposed to be a gap between these components and this enclosure, so that when it closes, there is no interference and it latches onto it. Uh, and what's happening is like when this lid is closing, sometimes either this part is getting too high so that uh, there is a gap which is being created over here, and it is only happening in some of the parts. So let's see what's the issue. Now these are some of the dimensions which are given. Overall, if I consider it to be a datum, uh, this particular dimension is 46 with a bilateral tolerance of plus minus 1. And this all components starting from here, we have 20 with a bilateral tolerance. And then we have 4 to 5, which is a range, then a unilateral tolerance. And then we have again a bilateral tolerance. So before starting any stack up analysis, the first thing which we need to do is convert all this unilateral or range tolerances into bilateral tolerance. So let's do it. Convert it into bilateral tolerance. Converting it is very straightforward. So let's do it like 20 remains 20. The range is 4 to 5. So what's the midpoint of 4 to 5? It's 4.5, and the tolerance is 5 minus 4. That's 1 divided by 2. That's 0.5. Uh, Similarly, if we look into the unilateral tolerance, what is the tolerance? Total tolerance is 2 divided by 2, that's 1. So unilateral tolerance is plus minus 1. And then you add that plus 1 to 10, you get like 11. Uh, it's very intuitive also. And this is remains bilateral tolerance. So the first thing we did was to convert unilateral and other tolerance to bilateral tolerance. Second is we have to define loop, which is again very straightforward. Let's look into it. The gap, the starting point of the gap we have defined as A, the ending point we have defined as B. So when I say A to B, it's a vector, so it will be like from this direction. And when I say B to A, it will be from this direction, right? So it's first we labeled the gap, we defined one as A, one as B. It's completely up to you. It does not matter at the end what sign you choose. Dimension A to B here I'm assuming to be positive, and dimension B to A I'm assuming to be negative. Uh, then this is a very standard table. Uh, you put first column as positive. I normally try to make it in Excel so that you can like iterate it multiple times. But here it's in PowerPoint. But the key point is Only we have one dimension which is going from A to B, like from here to here, 46. For negative dimensions, like from B to A, if I come from here, we have 8, 11, 4.5, 20. We rotate down here. Tolerances, no matter whether it's from positive or negative, we just put all bilateral tolerances here. The last row is a summation of it. So total positive side is 46, total negative side is sum of all this, and total tolerance we add up. Key point to note down is like we have to start from the same point. So this datum is same. So that's why when we compare it, it makes more sense. Uh, Now, what will be the nominal gap? As also you can be see, right? Nominal gap will be this minus all of this. So this positive minus all of this. So that is 2.5. And what will be the maximum gap? Maximum gap will be this nominal gap plus minus this tolerance. So the biggest one will be 2.5 with a gap with the additional 4.5. So we can have a gap of 7, which is good. If we have a bigger gap, the lid will close. Minimum gap. Minimum gap is negative, as all things uh, until and unless we are in imaginary worlds, all real objects have a positive value. You cannot have a negative length. So negative means that gap does not exist. It means it's a case of interference. So that's what happening. We evaluated it and we found that this is the minimum gap. So far it's very straightforward, but the issue mostly is being asked is how do you resolve it? So let's look into it. One way to approach about this problem is reduce all the tolerances by half. Let's look into it. How does it affect? So this is the approach one where uh, like normally the first intuition everybody has is like why not tighten the tolerance? Let's do it. So we reduce all the tolerances, like these were the earlier tolerances and now we have reduced everything by half. So the total tolerance value earlier was 4.5, now the total tolerance value is 2.25. And what is the effect of that? So nominal gap remains same because we have not played changed any nominal values. Maximum gap is reduced, which makes sense because we have reduced the tolerances, so the variation is going to be less. And minimum gap, see now although there is a tiny gap and it's positive, so it means it's not going to interfere. This strategy works. The only question here is when you ask for a reduction in tolerance, generally the cost increases. The picture is covering here, but it says that yeah, the drawback of this whole thing is higher cost because machining people are going to ask you for more cost. So until and unless it's justifiable, yeah, this approach can solve the issue, but it at a higher price. The second approach could be just change the nominal value. So one of the nominal value, the easiest one could be you can just make a like a more clearance for this enclosure. So you just increase this value by 3. Rest everything remains same. So let's see the effect. Now what changes? Nominal value change. Nominal value is affected by this nominal value. So now the nominal value is high. Tolerance remains same. So now maximum gap is increased and minimum gap is 1, which is positive. So another way to solve is without changing the tolerance is increase the nominal value. We increase the positive value and similarly you can decrease the negative values to arrive at the same conclusion. Uh, so these are like two approaches which people take. One is cost effective and another is not cost effective. With this approach, you have to make sure that you are not compromising on functionality. You have to again make sure that when you shorten this, you are not compromising on any of the previously existing capabilities. Uh, let's say uh, there are a few follow-up questions which people should ask or generally ask or you will encounter. Uh, what we were doing is the worst case stack up analysis. But are there any factors which affect worst case stack up analysis? So one thing to note is whatever we did was at room temperature. At higher temperature, we know that the length changes by thermal expansion, L alpha delta T. Yeah, if something is going at a high temperature, create another column which takes into account the temperature, and their worst case will be the length of that particular part at a higher temperature, which is something, yeah, if you have a temperature constraint, like make sure you include that particular analysis. Are there other methods of stack up analysis suitable for mass production? So yeah, like right now we talked about worst case stack up analysis. There is a root sum square method. It's a statistical method, so it means like it will say that as long as you are happy with some of the parts being not fitting well, but majority of them are fitting well, then you can go with this root sum square method. Worst case is like we don't want a single worst case. Uh, Preparing for the worst case. But whatever like we saw is on the basis of worst case stack up analysis. Yeah, this was it. Yeah, it's very standard thing, but everybody should do it for whatever part design, and it's normally being asked. Next is general GDIT. We will discuss in next part. Bye.